Hello friends, in this video we'll talk about some important problems or 2 to 3 problems on Taylor and Laurent series expansion, and you make sure that you do understand these 2 3 problems very well, because these are very important problems in terms of they will cover mostly whole topic itself, so they are chosen such a way that it will summarize the whole concept and the problem solving method of Taylor and Laurent series expansion. So if you are done with it, if you understand them very well, I'm sure that you will be able to any of the problems which are related to Taylor's and Laurent series, even in asked in the entrance exams. Alright, so let us start. But before that, let me remind you that let me take the complex plane here, and I have mentioned about this before, but in case if you have forgotten, I'm just giving a quick reminder on this, is that in the complex plane, this is the real axis we defined, and this is the imaginary axis. Real axis generally is an x coordinate, and the imaginary axis contains y coordinates. Also, the complex number is defined by z equals x plus iy, in which x coordinate is defined on here and the y coordinate is on this axis. Alright, once we have this complex number, we can always have a function of z which we call f of z, and we check about the analyticity of these functions. We have studied a lot about how to find out whether the function is analytic or not, and other topics related to them. So let's not get into them, but quickly just be prepared for the series expansion problems. So we consider that the function f of z is analytic here, but in some pattern. So by following some patterns, we will be able to decide that whether we should apply a Laurent series or a Taylor series for a particular case. So how do we decide that? As we have seen earlier, that suppose you have a function f of z which is analytic within this circle, within this boundary, in this region. If it is analytic, then you can always have some point z equals z0, about which you could do a series expansion, and in this case, in this particular case, you will perform Taylor series expansion. So Taylor series expansion is always performed when you have a function which is analytic within this closed region and it has no any singularity inside the region. If this kind of pattern you find for any function f of z, then you will always perform a Taylor series expansion. When you have a function f of z which is analytic in this kind of pattern, which I am just making it here right now, in which, I'm sorry the circle I didn't draw well, but I hope you will imagine. So in this region, I have this circle 1 and 2, also I can call it curve 1 and curve 2, and in this case, if I have the function which is analytic in the region between the two circles, so you see that this is a ring shaped or annulus region, annulus circle. So if the function is analytic in this pattern, then you will always perform a Laurent series expansion. These are very loosely given definitions. I am doing that because we have already defined the Taylor and Laurent series before, so therefore I'm giving a very loosely structured definitions here, just in order to recall and make sure that we understand the basic concept behind when to use Taylor series and when to use Laurent series. Alright, so in brief, in summary, Taylor series expansion is always performed when the function is analytic within the closed region and that region does not have any isolated singularity. Then the Taylor series expansion can be performed about the point z equals z0 within that region. When we have an analytic function which is analytic between the two circular region, between the two curves, and that is the ring shaped or the annulus region, then we always performed a Laurent series. Alright, so having said that, now let us quickly go to the problem. Oh yes, and one more thing, that we just saw that we can do the Taylor and Laurent series for these two cases. But then the another question is also here, that how do we expand? So we already saw that also, that for Taylor series, so with this condition which we have shown here, that we have a function, let's say f of z, which is analytic within this region about z equals z0, then the Taylor series can be expanded about z equals z0, which is given by f of z0 plus f prime of z0 into z minus z0 upon 1 factorial plus f now double prime of z0 into z minus z0 whole square upon 2 factorial. I hope you are already seeing the pattern. F triple prime and then cube of this bracket upon 3 factorial and so on. So this is the series expansion, the Taylor series expansion about z equals z0 for the function f of z, provided that we have the analyticity like this. For the Laurent series, briefly I can write, so this is for Taylor series. For Laurent series, we can have, again it is about z equals z0, okay, and so this is the point z equals z0. Alright, so I can do a series expansion as in briefly I can write n equals 0 to infinity an into z minus z0 to the n, okay, plus sigma n equals 1 to infinity bn upon z minus z0 to the n. So you see here that in Laurent series we have two terms, the series of two terms. This is also a whole series itself and this is also a series, but in the Laurent series we have one series which has the z powers in the numerator and then we have z powers in the denominator. We will look into this also when we will be solving the problem on Laurent series, but I'm just making I have highlighted the fact that you can see the difference between the Laurent and Taylor series already. In Taylor series we have the power of z only in the numerator like this, okay, it's z minus z0 to the power n. Here you can see that. But in Laurent series there is one extra part along with this, and that is you have powers of z which are in the denominator as well. So that's where the Laurent series comes. Okay, so whenever we have 1 upon z to the power something, you automatically know, I mean you already know that there you have a Laurent series. We will look into this, but this is something I'm highlighting so that you can keep in mind, and you can already start seeing the difference between the Taylor and Laurent series themselves. Alright, so having these definitions now, we will see how to solve the Taylor series problem. Okay.